Okay, so we're going to move on to thermal expansion now. So, Karina, give this a read from her. Thermal expansion.
Thermal expansion. In a solid, the molecules are held closely together.
Wait,
When they,
did you remember that? Did you remember that solids are really, really close together? Like they don't really move much. Did you remember that from last class?
yes, and then gases are freely movable,
And
and
look,
then liquids are partially together.
exactly. And when you heat up something, you add in what kind of energy to it.
Kinetic energy.
And if you have kinetic energy, that means you're moving about,
Yes,
and if you start to move about and spread apart, will you take up more volume or less volume?
more volume.
Right. I think you can see how thermal expansion is going to work then. Because in a solid, the molecules are held closely together. But if you heat up something, like, kinetic energy is added, the molecules vibrate faster, and this would cause them to move apart and increase their volume. So you can think about it and it'll make sense. So, Karina, what do you think would be the case? Let's just say I have this metal slug, right? And this metal slug is at 10 degrees Celsius. If I heat up the metal slug, will it stay the same size or will it get bigger?
It'll get bigger.
Yes, it will get slightly bigger. And that's because when you heat it up, you add kinetic energy, the molecules will vibrate faster and they will move about. And that would increase the volume. So the volume would increase by a slight amount. So that's why you see here, um, in this example, before heating, the ball could pass easily through the ring. But after it heated, it can't go through because it would have expanded a bit. Tell me if you understand that.
Yes, sir.
Okay, nice. Now, in the exam, they will ask you what thermal expansion is, and they will also ask you to state some examples. And some examples would be creaking roofs, power lines sagging on hot days due to expansion. Let's see how that would work. Zachary, if you have two power lines here, right?
Yes, sir.
And normally, like the wire running from one pole to the other pole, it wouldn't be sagging that much.
Yes, sir.
Wouldn't be sagging that much. But on a hot day, what has happened is, tell me something, right, Zachary? What material is the wire made out of?
Metal.
Yeah, metal. And metal is a good, and metal is heat up really fast.
Yes, sir.
If it's gonna heat up really fast, it's gonna gain kinetic energy. The molecules are gonna start to vibrate, and they're gonna take up more volume. So Zachary, do you think it's gonna remain this length, or do you think it'll get longer in the heat?
It will get longer when it heats, sir.
Exactly, but the distance for the poles is going to remain the same. And if the distance at the poles is going to remain the same, it's not going to hold the wire taut anymore. It's going to start to sag because that extra length had to go somewhere. Understand? I trust that.
Yes, sir.
Karina, you understand that? That on a hot day the power lines go sag because the length would increase.
Yes, sir.
Okay, nice. They could ask it any exam. So take note of that. All right. Running warm water over a jar lid that is too hard to open. So Karina, now you know if you're struggling to open a jar, what you could do is you could run it on a hot water and you should be able to open it then because the lid will actually expand and it'll make it easier to open. So the more you know. Another one is when beverages get warm, the CO2 bubbles expand and escape. You'd probably see that, when you take a cold beverage out of the fridge and you rest it down in your room. Let me just say your room hot, right? Let me just say you don't have AC. Karina, and just like you see a bunch of little bubbles like just rising to the top. You see that?
Yeah, and then the bottle starts to swell.
Exactly. That's because the CO2 that was dissolved in the solution is actually escaping as a gas. And Karina, if the gas is escaping, it would occupy more volume, right? Remember, when you apply heat, any molecules that vibrate more.
Yes.
Yeah, so the CO2 that was dissolved in the liquid is going to start to escape and it's going to start to rise up because it's getting kinetic energy. And eventually, it will cause the bottle to swell because, Karina, it's taking up so much volume. And when you open it, it will overflow, right? Because the CO2 wants to violently escape. Do you understand these concepts here?
Yes, sir.
Nice. So, guys, if you was ever wondering why a hot Coke would be flat, this is why. Because if it's hot, most of the CO2 that was dissolved in it would have escaped. So now you know. If you want to keep a beverage as carbonated as possible, leave it in the fridge. Don't expose it to the elements. So are you all okay with thermal expansion? Tell me if you're okay with the concept of thermal expansion.
Yes, sir.
Yes, sir.
Okay, bimetallic strips now. Now, bimetallic strips is actually an application of thermal expansion. So, Karina, make a guess. Do you think all materials expand at the same rate?
Sir, can you repeat?
I want you to take a guess, a logical guess. Do you think all materials would react to heat the same?
No.
No. Do you think all materials would expand at the same rate when exposed to heat?
No.
No, because they're different, right? They have different structures and whatnot. So when you're using a bimetallic, first of all,
Oh
Korean,
my
what is
so bad, Mama.
you remember
Oh my
bimetallic?
so bad. Oh,
Say that again?
sorry, sir.
Yeah, you were saying something?
Oh no, not you, sir.
Oh, okay. Karina, what does bi mean? Not in that
It
sense.
can go. It can go both ways.
Yeah, right? Now, bi actually means two. Bi means two, right? So, as the name suggests, bimetallic means two metals. So, I'd like you to read bimetallic strips. Read that for me.
The bimetallic strip consists of two strips of different materials which expand at different rates as they are heated. Usually steel or iron and copper or brass. The different expansions force the flat strip to bend one way if heated and in the opposite direction if cooled.
All right.
Below is the normal temperature.
All right. So, Karina, let's try to understand what's happening there. So, Karina, you just told me that different materials would expand at different rates. So, a bimetallic strip works by using two different types of metals. Why? Because if you expose them to heat, they'll bend at different rates. So let's look at some examples. So we're using brass here on top and steel in the bottom. Now, Karina, at normal temperature, are you seeing any thermal expansion?
No.
No. But if you heat it up, right? If you heat up this bimetallic strip, you notice that it's bending downwards. Seeing that?
Yeah.
Right. Karina, if it's bending downwards, which one do you think is expanding more? The brass or the steel?
The brass.
Right, because if the brass is expanding, it will force it to move downwards. That makes sense?
Yeah.
Right, so hotter than reference temperature is just like room temperature or something. So the brass expands more and its greater length puts it on the outside of the curve. Zachary, do you understand that if brass is more likely to expand, then that length is going to increase more. And as such, it would take the outer perimeter.
Yes, sir.
Okay, nice. And let's look at a colder temperature than your reference. So brass contracts more and its shorter length puts it on the inside of the curve. Let's try to understand that. So Zachary, if
Yes.
brass expands more, obviously it would mean that steel expands less, correct?
Yes, sir.
Right. So it would be more prone to actually contracting. So when I expose them to a cold element, the one at the bottom is going to contract. And if this length is slightly decreasing, it will force it to pull upwards. Can you see that intuitively? Does it make sense in your head?
Yes, sir. It makes sense.
Okay, nice. Right, so Karina, how are you feeling about bimetallic strips?
Fine.
Okay, I'm going to give you an example here. I'm gonna call this metal A and I'm gonna call this metal B. All right, let's just say that B is more prone to thermal expansion. Let's just say that is it expands at a greater rate. So Karina, if I apply some heat to this, let me just draw Sukunya here. One second. All right. I draw like a really bad Sukunya. um, Tell me, Karina, if I apply heat to this bimetallic strip, which one is going to bend more? And what I should say is which one is going to expand more? Is it A or B?
B.
B. If B is expanding more, right, and A is expanding less, do you think it will force it to move downwards or force it to move upwards?
Force it to move upwards.
No. If B is expanding more, look at where B is. B is at the bottom. Karina, where's A?
At the top.
Right. Is A gonna expand as fast as B?
No.
No. So A is going to remain short, B is going to remain long, and since B is getting long and is attached to A, it's actually going to stretch it like this. It's gonna stretch A, push it downwards. Zachary, you understand that?
Yes, sir.
Okay, so Karina, no worries. You'll get it. You'll get it. Don't worry. Um,
No, sir. Understand. I understand.
I hate this new Good Notes update. I don't know if I'll always use Good Notes, but like Good Notes is like horrible now, bro. Absolutely atrocious. Right. So Karina, let me make it a little more clear for you. I really want you to understand this. So do you understand that after heating, the one on the bottom will get a little longer?
Yeah.
Now, Karina, if this one get a little longer and it's attached to this one, so like they attach together, right? If this one getting longer and this one already getting longer, wouldn't this one pull on this one because at the end of the day, and this one increasing, even if this one not increasing as fast, they still attached together. So this one will pull this one, and it will pull it in this manner because this one is longer. Generally speaking, the one that expands at a greater rate is always going to be on the outside. So Karina, can you see that the longer one is going to pull on the shorter one and is gonna actually become a curve?
Yes, sir.
Okay. Taking your word for it. Trusting you here. So as you can see, the green one is slightly longer. Because it's slightly longer, it's going to pull the blue one, which is not expanding as fast, downwards. All right, Karina, what if I were to cool this thing down? What if I were to put it in the freezer? Tell me which one, if B is more prone to thermal expansion, which one do you think is prone to thermal contraction?
A.
A. So, so the size of A is actually going to increase or decrease when you put it in your fridge.
Increase.
Okay, when you put things in a fridge, are you adding kinetic energy or are you extracting kinetic
Oh,
energy?
no. Yeah, you extract it.
Right. And if you put something in the fridge, the molecules will they move faster or will they start to slow down?
It'll start to slow down.
Right. And if it's slowing down, the vibrations will be less, so it would take up more volume or less volume.
Less volume.
Exactly. So A is gonna get shorter, and it's gonna get shorter at a faster rate compared to B. So this is gonna get short, and this is gonna remain the same length. So what direction do you think that's gonna move up in? Move up or move down?
In the up direction.
Right. Zachary, let me know if you understand this. Or like, yeah, a little confused about it. Zachary,
Yes, sir. The Wi-Fi cut off there.
tell me if you're confused.
Nah, sir.
So, Jalen, you don't mind if you don't mind, you could go over it like one more time.
Okay, no problem. So, Jalen, I'm seeing that different materials would expand at different rates. So anytime you heat up something, you're adding kinetic energy, and as a result, the molecules on the inside, they're gonna try to move more. And if they're moving more, they're gonna take up more volume. So the point is, when you heat something up, it's going to expand. Now, all materials expand at different rates. So in this example, we're using it in a bimetallic strip. A bimetallic strip is made up of two different types of metals. This is made up of brass and steel. So at normal temperature, the molecules have a normal amount of kinetic energy, right? So it's just perfectly straight. But if I were to heat it, if I were to heat up the bimetallic strip, notice what happens here. Notice what happens.
It bends downwards.
Yes, it bends downwards. And let's try to understand why that happens. So, children, if so the brass is on top, right? The brass is on top. If the brass is on top, right, and it expands more, the length on top is going to increase. Can you see that?
Yes.
Okay, and if the length on top is increasing, is the length at the bottom increasing as fast?
No.
No. So the top one is going to get longer at a faster rate, and the one at the bottom is kind of going to remain short. So what end up happening is that the top one pulls it, it gets longer, right? But because the short one is at the bottom, it kind of restricts it, and so it would move downward because the one at the bottom is remaining shorter. That kind of hard to understand.
No, I understand.
Okay, So whichever one is longer, it will control it. Like watch this again, right? So this is longer here, and it's connected to a shorter length. The only way it could move is to bend like this, bend downwards.
Mm-hmm.
Now, colder than reference temperature, brass contracts more and is shorter. So the brass would contract more and is shorter. So, okay, so I think I told you something slightly incorrect. Whichever one would have a greater thermal expansion rate, it would also contract more because it's more prone to temperature changes. So, Jadon, let me just explain this back for you, right? So, brass and steel, you understand this example? The top one would get longer, and because the bottom one was remaining the same length, it would have been pushed downwards.
Yeah.
Okay. Now, since brass was more prone to thermal expansion, it will also be prone to thermal contraction. So if I were to put this in a freezer, notice what happens with brass. The brass is going to get slightly shorter. So if the brass is getting slightly shorter and the bottom one is remaining slightly longer, you can see how it's going to push upwards
Mm-hmm.
because this one is longer in the bottom now. So whichever one is longer, it will kind of dictate what direction you go in. So I hope you understand that.
Wait, do you mean that by like longer in the initial state or just by the temperature change? So as
Well, both will
like
be the same. Both will be the same length at the start. Both will
at
be
the
the
start,
same length.
and then the temperature change causes it. So hotter would cause the brass to go down, and colder would cause the steel to go up, basically.
Not so fast.
But also with the temperature, as you said, when it's hot, the steel starts to shorten,
No, no,
and
no.
the
The steel,
brass.
no, no. The steel is not shortening.
Mm-hmm.
It's not
Or the
shortening.
brass. Is it that the
Both of them are expanding. Both of
yeah?
them are expanded. The thing is, the brass is expanding faster
That's
than
a
the steel
faster
could
rate.
expand. Yeah.
Okay. Yeah.
So what's happening is that the brass would get longer compared to the steel,
Okay.
and so it bend downwards. And when you put it in the freezer, right,
Mm-hmm.
it's gonna contract more. And if it's contracting more, then the top length is gonna get shorter than the bottom length. It's gonna pull up. Some of you understand that.
Yeah, I understand.
All right, let's revisit this example. Make sure we understand it. So I said that B is more prone to thermal expansion, right? I'll make a little note. So Karina, sorry about that, right? Whichever one is more prone to thermal expansion will also be more prone to thermal contraction. So B is also more prone to thermal contraction. Right, so Karina, let's run through back this example to make sure we fully understand it. Right. Okay, so Karina, at the start, at the reference temperature, both of them is the same length. You agree?
Yes, sir.
Okay, cool. When I heat it up, which one is more sensitive to heat? A or B?
B.
B, right? Okay. If B is more sensitive to heat, which one is going to get longer?
B.
B. B is going to get longer, right? Now, if B is getting longer, is A increasing at the same rate as B?
No.
No, it is not. So let's try to imagine what's gonna happen. This is remaining short, and this is getting really long. What do you all think would happen?
We'll start to curve downwards.
it'll start to curve downwards. Let's see. Now, this example I'm giving you all here is the opposite of the first example. So, Karina, do you still think it should move downwards? Let's look at this example. Is opposite examples, right? So, Karina, in this example, we understood that the top one was expanding at a greater rate. So, Karina, if the top one expanded at a greater rate and it moved downwards, what do you think is going to happen here? In this example, the bottom one is expanding at a greater rate.
Yes, sir.
So, Karina, this example and this example, they're opposites of each other, right? So,
Yes, sir.
in the first example, the brass would have got longer in a shorter time than the steel. In this example, I'm saying that B is going to get longer than A in a shorter time. So do you think it should curl downwards or curl upwards?
Yeah, I don't really understand. Before you said the B would just curve downwards and then the A is still attached to it. So it would just like move at a slower rate
That was a mistake.
of expand.
That was a mistake.
Oh,
Yeah, that
okay.
was a big mistake, right? If you analyze this thing, E is going to remain shorter and B is going to get longer. Where's that extra length going to go? That extra length is going to cause it to move upwards. Because these two examples are opposites of each other. Karina, watch. In this example, which one expanded at a greater rate? Was it the brass or the steel? In this example,
The
the brass. And we saw that when we applied heat, it moved downward, right?
yes, sir.
Okay, in our example here, which one is at the bottom?
B.
And if I were to wait, I'm gonna use the same metals. I'll use the same metals. So I'll call this brass. This is brass, and this will be steel. No, so I'm changing the order. Right, steel. Yeah. So Karina, if I were to swap the position of the metals, right? The opposite of what you're seeing here should happen. The opposite. So, Karina, if I apply heat, isn't the brass going to expand faster than the steel?
Yes, sir.
Yes, we know that. However, it's attached to the steel. And so it will not move straight, it'll actually move upwards because the one on the outside needs to be longer than the one on the inside. So it's actually going to look like this. It's the opposite of the example at the top. You'll see what I mean. Karina, when you look at this example, which one is slightly longer? Is it the steel or the?
The brass.
Yeah, exactly. It'll move upwards. And Zachary, for the last time, if you were to apply, if you were to like say put ice on it or like put it in the freezer, since B, which is brass, is more prone to thermal expansion, it will also be more prone to thermal contraction. So what's gonna happen with the brass?
So it will contract and it will go downwards.
Yeah, it will contract and it will go downwards.
Yes.
That's correct. And at that rate, which one will be longer? The steel or the brass?
Steel.
Right? The steel will be longer.
So, sir, the steel isn't the one that's prone to the thermal contraction, right?
Wait, No, let me explain something. So, Karina, you see how brass is sensitive to thermal expansion?
Yeah.
That also makes it more prone to thermal contraction.
Okay.
Generally speaking, softer materials, I believe, they are the ones more prone. Let me just verify that. Right. Softer. Yes, that is the general rule. So the softer the metal is, the more likely it will be prone to thermal expansion and thermal contraction. Yeah. So, Karina, that's the general rule. So the softer the metal is, the more likely it is to expand and contract. So, Karina, in this case, brass is the softer metal. So it'll be more prone to thermal expansion and thermal contraction. So, Karina, do you understand that after I apply an ice block or like just probably this in the fridge or something, which one is going to contract more? Is it steel or brass?
Brass.
Brass. So the brass's length is gonna get shorter than the steel's length because steel isn't as resistant to temperature changes. And as such, it's going to curve downwards. So sorry about the mix-up. Hope we understand it now. Everybody okay with that?
Yes, sir.
All right. So the general rule, I'll write the general rule here. In general, I should probably write neater. That's really scrappy. In general, softer metals are more prone to expansion and contraction. Zachary, does that make sense? When you think of softer metals, right? Do you think their intermolecular bonds are stronger or weaker? Like when you hear soft metal, what do you think? Weaker. And if it's weaker, wouldn't I require less heat to increase the movement? Because
Yes.
the bonds are already kind of weak.
Yes, sir.
Yeah, so it makes logical sense. Right? The softer the metal, the more prone it would be to expansion and contraction. So that was that. Let's look at an example of something here. It's used in a circuit. All right. So in this circuit, the bimetallic strip, when heated, would bend towards the contact to allow electricity to flow. This effect is used in a range of mechanical and electrical devices, such as thermostats and fire alarms. All right, let me test you guys. So, Karina, we have two metals here. I'll call the first metal, metal 1, and I'll call the second metal, metal 2. They are saying that when we heat it, like if we apply heat, they are saying that it would bend upwards. So tell me, Karina, see if you can figure out which metal is more prone to thermal expansion.
Metal 2.
Metal 2. Does everybody agree or disagree?
See, I agree.
I would agree as well. And that's the same scenario with the example here. Watch. When the brass, if you put the brass at the bottom, right? The brass was the one more prone to thermal expansion. So the length at the bottom would have increased, but the length at the top would have remained a little shorter. So it'd have pushed it upwards. Right? So in this example, metal 2 is more prone to thermal expansion and thermal contraction. Yeah. And guys, if you expose this to the cold, what would happen to the bimetallic strip?
It'll contract.
Right. So the one at the bottom would contract more, and the one at the top would contract less. Right? And this would force it to move downwards. We okay with that?
Yes, sir.
All right. Jadon, let me know if you want me to re-explain that.
So you hear me?
Yeah, I'm hearing you.
Rain is like killing my mic right now, so I can kind of barely hear you. But yeah, you could, if you could go over it, please.
All right. So Jadon, where did I lose you from? Tell me where I lose you from.
It's not that you necessarily lose, man. It's just that like after, well, I understood when you switch the the metals or whatever, and I guess it's from when you were explaining the circuit, the like circuit thingy, that little image down there. Yeah.
All right. So Jadon, this circuit you're seeing here is a circuit that would be used in a thermostat or something. Do you understand that a thermostat, you want the thermostat to go off when it's hot? Like when, in the event of a fire or something, like a fire alarm or something. The circuit will be used in those conditions. If you have a fire alarm, and you would want the fire alarm to go off if a fire starts.
Yeah.
Okay. So look at this, Jadon. For the circuit to go off, and the circuit needs to be complete. Like it mustn't have any gaps in the circuit.
Yeah. No.
Okay, right now, um, is there a gap in the circuits?
Yes, there is.
Okay, and you would want that when you apply heat, you would want the bimetallic strip to go up or go down.
You'd want it to go up.
Right, so that this connection would make contact with this.
Yeah.
Yeah, yeah. So my question was, I just adding an additional question. I asked you guys which one, if this is metal one and this is metal two, I asked which one would be more prone to thermal conduction and thermal expansion.
Basically asking which one would go up and which one would go down.
No, asking you which one would, if I apply heat, which one would get longer first? Like, okay, which one would expand at a greater rate?
Metal too.
Metal 2, correct. If metal 2, and it makes sense, right? Metal 2 will
Yeah.
get longer at a quicker rate than metal 1,
Mm-hmm.
and as such, it's going to bend upwards because metal 1 is slightly shorter than metal 2. So it's going to bend upwards. I hope you understand that.
Yeah,
You?
yeah.
Right? So if they ask you in what application would you use bimetallic strips, you would say that you'd use it in thermostats and fire alarms, and they might give you a circuit. All right, let's move on to the greenhouse effect. So again, Karina, since you have the exam, I'm placing emphasis on you, right? What about the rest of you guys? Does the rest of you guys have physics exam anytime soon? Zachary, I think you had told me your exam's done or something. Was that you?
Yes. Physics finish.
Okay. Well, Karina, read the greenhouse effect for me.
Greenhouse effect. Whether or not radiated heat can penetrate glass depends on wavelengths. Heat is mostly carried by infrared waves and some UV. Short wavelengths have higher frequencies and higher amount of energy, and therefore more penetrative ability than long wavelengths. Waves lose energy as they reflect off surface. Therefore, the short wavelengths that were able to penetrate the glass cannot escape. Once they convert to long wavelengths when they are reflected inside.
All right, you probably read that and you understand like what 40% of that because like they're using some big words and things. Then be honest, how much did I actually understand?
Most of it.
Most of it. Okay, great. Well, I'm just gonna go in all more in detail, right? We start off with the sun. Karina, the sun, doesn't the sun emit visible lights and it emits infrared and ultraviolet lights? Yeah.
Yeah.
Okay. Which is the one that carries heat? Is it visible, infrared, or ultraviolet?
Infrared carries more.
Infrared carries the heat, right? Heat is mostly carried by infrared rays and some UV, but mainly infrared. So let's understand, let's run through a scenario, right? Generally speaking, high energy would correspond to a shorter wavelength. Right? And it would also correspond to greater penetrative ability. Consequently, when we're talking about low energy, it would correspond to what, Karina? What do you think? Low energy. If high energy is shorter wavelengths, what do you suppose low energy would correspond to?
Longer wavelengths.
Right? Longer wavelengths. And in terms of penetrative abilities, ability to pass through materials, do you think it's going to be greater or less?
Less.
Right. Or weaker. All right, let's understand something, guys. So, Karina, the sun emits heat energy in the form of infrared that would reach the earth, right? Let's just say you have a metal sheet or something, and you have something. Wouldn't that absorb the heat energy from the sun?
Yeah.
Okay, but when it absorbs heat energy, is it the same temperature as the sun, or is it like much cooler than the sun?
Much cooler than the sun.
Exactly. So you would get the thermal energy from the sun, right? You would get, I should really draw that really short. Okay. So you have a short wavelength here, and that's directly from the sun. Now, Karina, when that material absorbs the heat, wouldn't it only be absorbing like a very small fraction of heat?
Yes.
Okay. And whenever you heat up something, doesn't it emit back heat? Like think of like a hot plate, or like you're cooking food and you have a hot pan. And if you put your hand over the hot pan, you'd feel the heat radiating off.
Yeah.
So tell me, that heat that is radiated off, is it as strong as the surface temperature?
No.
No, not at all, right? So the heat energy that's being re-emitted, do you think it's high energy or low energy?
Low energy.
Exactly. So it's low energy, it's a longer wavelength, and it's weaker penetrative ability. And if it's a weaker penetrative ability, do you think it'll be able to escape things like gas? Like pass through gas? I mean, pass through glass?
No.
No, it won't be able to pass through glass. That's the general concept for the greenhouse effect. I'll re-explain that. Zachary, you there?
Yes, sir.
Okay, so do you understand that the sun emits high energy, like really, really high energy in the form of heat energy, and heat energy is given in the form of infrared rays. Infrared
Yes,
rays
sir.
will carry the heat.
Yes, sir.
Now,
Yes, sir.
we would feel the heat, correct? And you would feel the heat?
Mm-hmm.
Right. So let me give an example with galvanized. Let's just say you have a galvanized sheeting over here, like on your roof or something. That is going to absorb the energy directly from the sun. Now, the energy from the sun is high energy and it's going to be a short wavelength. Zachary, isn't that going to heat up your roof?
Yes, sir.
That's gonna heat up the roof, right? So the roof is gonna heat up. Now, Zachary, the energy that's going to be re-emitted by the galvanized, is it going to be more than the energy that causes the heat up, or less than
No,
the energy that causes the heat up?
maybe less than so.
Exactly, right? Because if you put your hand over a galvanized, chances are it's probably not going to be as hot as if you actually touch it yourself. Like, if you touch the galvanized directly, that's going to be a lot more hotter than the energy that's re-emitted. So can we
Yes,
both agree that only a small amount of energy is re-emitted?
yes, sir.
Exactly. So a small amount of energy is re-emitted. So you're going to have longer wavelengths leaving the galvanized. That makes sense?
Yes, sir.
Now, the longer wavelengths, could it penetrate materials like glass or whatnot?
No, sir, because it weaker.
Exactly. It's very weak. You think that that very weak heat could pass through anything? No, I can't really pass through anything. So if you have like a metal, if you have like a glass cage, in agriculture, you have greenhouses, right? I'm not sure if you ever see like those glass houses where they would have plants and things in.
So basically the greenhouse trapping the heat, and since the when they trap it, they wouldn't be able to remit because the energy levels lower.
Yeah, exactly. Right, exactly. The shorter wavelength radiation from the sun is going to easily enter the glass inside the glass house, right? But when it heats up the contents on the inside, the heat that the contents re-emits is of a low energy and is a longer wavelength. So that re-emitted energy, it can't really leave the glass house. So the heat builds up over time. And that's what causes the greenhouse effect. You understand the concept, clear?
Yes, sir, that makes sense.
Okay, nice. Because the whole concept, right, is that when you heat up something, it would get hot. But the heat that it re-emits is not a lot. It's really not efficient. And so the heat that something re-emits is very low. And so that can really escape. Yeah. Think of like Zachary, think of like when you're cooking. And when you're cooking and you heat up the bowl or whatever, a pan or something. And the pan is reached like 100 degrees Celsius or something. Like real hot.
Yes, sir.
Yeah. So the pan or whatever is getting real thermal energy. But is it re-emitting that thermal energy? As much thermal energy?
Mm-mm. It will
No.
remit less energy.
Yeah, like a lot less. If you take off that stove, right?
Mm-hmm.
If you're standing like what 6 feet away from that pan, you're gonna feel that heat?
Not really.
No. So you think that you're emitting plenty energy?
No, sir.
Nah. So the problem is when they heat up something, right? Most of the thermal energy is trapped in the medium. Only a very little bit is re-emitted. So that re-emitted ray is a longer wavelength and it gets trapped easily. That's the whole concept. You think you like have it unlocked,
Yes, sir.
Okay, let me give you like a really nice example. I did a really nice example here. Where is it? Um, all right, so Zachary, if you want to get technical into the equations, you can learn about Planck's constant, the wave speed relation, and it could actually prove it. It could actually prove that if you have a smaller wavelength, you'll have more energy. And if you have a smaller wavelength, you'd actually have a greater frequency. You could prove these things using these equations. I'm not sure if you're going to do physics and CAPE, but if you are, you'll see these equations. You'll see
Mm.
those equations,
All right, sir.
right? Yeah, so Karina, this is what happening, right? Karina, there?
Yes, sir.
All right. So this is what happening. The sun and we could both agree the sun is really, really hot.
Yeah.
So the sun will be emitting short wavelength IR light, right? And this would, do you think it would have trouble passing through the glass?
No.
No, that's real high energy. That could pass through the glass easily, very easily, right? So it passes through the glass, and Karina, the contents inside the glass is gonna heat up, right?
Yeah.
Right. So as you would see, now warmed, the objects give off long wavelength IR light. Karina, make sense of that. And the heat will start, and the heat from the sun will heat up everything on the inside.
Yes, sir.
Yeah, but do you think the objects gonna emit heat energy like okay, like the example I gave Zachary with the pan, if you take off the stove, the pan can be real hot, right? But like if you are 6 feet away from that, you're gonna feel the heat from that pan?
No.
No. So do you think the objects inside here are going to be emitting a crazy amount of heat? Or do you think they're gonna keep most of that energy? What do you think?
They wouldn't absorb all the heat.
They wouldn't, number one, they wouldn't absorb all the heat. And number two, they would re-emit a very small amount of heat. That's the word to use, re-emit. It wouldn't emit back much heat. So I'm saying the amount of energy that they absorb is if you compare it to the amount of energy it releasing, is really, really not a lot. It's like very low level amount of energy it releasing back. So the short wavelength IR light from the sun would pass through the glass, it would warm up the objects, and the objects would now give off long wavelength IR light. Right? So
Okay, sir.
you would see everything in the greenhouse absorbs the short wavelength IR and becomes warmer, right? So everything gets hot on the inside, but the warmed objects could only emit a very small amount of energy, right? So Karina, if the objects get hot, right, and now they're releasing energy, and the amount of energy that it would release would be very small,
Yeah.
yeah, and so that would be shorter wavelength. I'm saying shorter wavelength, that'll be longer wavelength. And if it's longer wavelength, can it leave the glass? Can it pass
No.
through the glass? No. And so eventually you're gonna notice that you have a bunch of long wavelength radiation just trapped inside here. And that would just build up the temperature over time. Do you understand the concept?
Yes, sir.
Okay, try to explain it to me now.
So the sun gives off short wavelengths, and it penetrates the glass for the greenhouse. And then all the plants will absorb a certain amount of energy. And because they can't absorb all the energy, they re-emit the energy back into the house. And it
No,
creates long wavelengths.
that's not exactly it. What you're saying isn't exactly correct. So, Karina, the objects would get heat up, right? They would gain heat energy. So as you will see, everything in the greenhouse absorbs the short wavelength IR light and it become warmer. So everything on the inside is going to become warmer.
Mm-hmm.
You have to say that the warm objects emit longer wavelength radiation. That's what you have to say. Like, because Karina, and we agree that the objects on the inside are gonna get warm, right? But are those warm objects going to be releasing a greater amount of heat? Like if you walk by a tree or something, will you be feeling the heat from the tree?
No.
No. So the whole point of this is the tree is going to be re-emitting a very small amount of energy. So you need to talk about the re-emittance. So try it back again. So, the sun heating it up, right? The sun would give off short wavelength radiation, and then everything on the inside would get hot. And the warm objects would what? What would the warm objects do?
reme um re re I can't remember the phrase now. So
Okay, re-emit. Re-emit.
re-emit
Mhm.
re-emit the long wave re-emit the radiation
No, re-emit long wavelength radiation.
long wavelength radiation.
You could say that, or you could say long wavelength IR light. Either one is fine. Yeah.
Long wavelength IR lights, and it wouldn't be able to penetrate back out from the glass.
Yeah, that could work. That could work, right? So you need to talk about the fact that it's not gonna re-emit much heat. So this was like a perfect answer for this question. The shortwave radiation from the sun passes easily through the glass and is absorbed by the black surface. The black surface becomes warm, but it is much cooler than the sun. It re-emits the energy as long infrared radiation, right? Cooler objects always emit longer wavelengths of radiation, and the long wave radiation cannot escape back through the glass. So it is trapped and the temperature inside increases. Do you all understand this answer?
Yes, sir.
Right, Zachary, like no confusion at all, right? Like you have it locked in. Talma.
Yes.
Okay, great. Jadon, tell me if you're confused.
No, sir, I understand.
All right, so Jadon, if we're talking about high energy, would that be long wavelength radiation or short wavelength radiation?
Yeah, man.
And now hearing you.
They'll be long, so
No, high energy is short.
high energy is short. Right. Okay.
Long energy is lower energy. Yeah, Jadon, watch this, right? I know it's not looking like it is short, but when we move on to waves, you'll understand why we're saying it's short. When we say wavelength, we're talking about the length for one full oscillation of the wave. So like this would be, right? So this would be one full oscillation here.
Mhm.
Wave. So I'm not talking about the size. I'm not talking about the size of the entire thing. A wavelength is actually the length of one oscillation, one crest and one trough. But when we do now, you go understand that a bit more. But Jaden, the point, what I'm trying to say is the sun is going to emit high energy, short wavelength radiation. So short wavelength, high energy, right? That could pass through nearly anything, right, Jaden? That's
Okay.
easily going to pass through the glass. So the sun, short wavelength, high energy, right?
Yeah.
That's going to warm the objects on the inside. Yeah?
Yeah.
Right. The objects on the inside, is it going to re-emit as much heat as it absorbed?
Mhm.
Okay, so how much you done? This amount of heat here, is it like small or like very, very large?
Well, as it passes through the glass, I guess it gets larger.
No, it doesn't get larger. Is
Well,
the same
initially, it just
is the same throughout. The energy from the sun is the
Mhm.
same throughout. So Jadon, the sun is emitting heat, right? The sun is emitting heat. That passing through the glass. And that's gonna be absorbed by everything on the inside.
Mhm.
So intricate both array that's gonna warm the objects on the inside.
Yeah.
Right, we could agree on that. Do you think the objects on the inside is going to re-emit as much heat energy compared to how much energy the sun emitting. Okay,
Yes.
I feel like I confused it. I'm gonna say that in a simpler way. Can we all agree that the plants and whatever they're gonna get warmer?
Yes.
Okay. Do you think the plants are going to emit what do you know what the word emit means?
Like like produce or like push out, I guess.
Yeah,
That's not
about
not
like
as
that.
well.
Think about
Mhm.
like give off. Tell me, Jadon, what do you think is emitting more heat? The sun or a tree that just get warmed by the sun?
I guess the sun.
Yeah, the sun.
Hmm.
Nothing could emit more energy than the sun in our
Yeah.
solar system. So the sun with short wavelength, right, radiation, it warms these objects on the inside, and these objects on the inside, do you think they are going to emit more heat energy or less heat energy compared to compared to the one that it absorbed?
It gonna emit more.
No, less.
So but okay, all right.
It can't emit more than it absorbed.
Okay.
Okay, Jilan, think of when you heat up something, right, like a pan. You heat up a pan.
Mhm.
Take off the stove. If you put your hand over the pan, you will feel some heat, right?
Yeah.
Okay. If you touch the pan directly, though, obviously that'll be a lot hotter, right?
Hmm.
Okay. So do you think the pan is emitting much heat energy compared to like if you actually touch it? Like,
No.
no. So can we both agree that the pan isn't actually releasing much heat energy?
Yes.
Because most of the heat energy is trapped within like the structure of the pan, like the metal and whatnot. Can we both agree that the pan not actually emitting much heat? Because like if you're standing 6 feet away from the pan, you're gonna be feeling any heat?
No.
No, but like the sun though. How far is the sun from it?
Oh, like very far.
Are we still feeling the heat energy?
Yes.
Yeah. So what do you think is going to emit more heat energy? The sun or a warm object?
The sun.
Exactly. So the sun is going to emit short wavelength radiation, and these objects that get slightly warm, they are going to release long wavelength radiation, which is of lower energy. That makes sense?
Yes.
Right. So you understand if you heat up something, it's going to, so if I make a note about it. If I heat up, if I heat, if I heat an object, the object is going to release yeah, so if you heat an object, the object is going to re-emit less heat than it's absorbed. And why, Jaden? The example with the pan, right? The reason was most of that heat energy is trapped within the structure of the object. Like when I told you, like if you touch a pan, isn't it going to be very hot?
Yes.
But if you're standing away from the pan, is the pan going to radiate much heat?
If you're standing away, is it gonna radiate much heat?
Yeah, radiate. Like, is it gonna are you gonna feel the heat from the pan?
No.
No. So what I'm saying is if you heat an object, the object is going to radiate. So re-emit means radiate, right? Re-emit basically means how much energy is it giving off. After it heats it up, how much energy is it going to give off to the surroundings? And it will always be less than the heat used to absorb it. I mean, what I'm saying, it will always be less than the heat you use to heat it up. So, Jadon, and you would use the burner to heat up the stove, to heat up the pan. Let me just say cooking eggs or something. And you would use the burner to heat up the pan.
Yeah.
What's the temperature of that flame?
What is the temperature?
At the flame, probably like 150 or 100
100.
degrees Celsius, right?
Yeah.
Compare that to the heat being radiated by the pan. Which one is more?
Flame.
Exactly, the flame. So I hope you can understand what I'm saying. If you heat up, the object is going to re-emit less heat than it's absorbed.
Yeah.
Right? So that's the whole premise of the greenhouse effect. The sun would emit short wavelength, infrared, right? This is going to pass through the glass. The objects on the inside are going to get warmer, and they are going to re-emit that energy as short wavelength radiation. What's in? As long wavelength radiation. And the long wavelength radiation, it cannot escape the glass house, so it's going to get trapped. So you start off with short, then that's into long, and the long can't escape. So it remains hot. Jadon, I'm going to do a recap for you, right? And then I'm going to move on. Jadon, short wavelength. Is that high energy or low energy?
High energy.
Right, this is high energy. And this would most likely come from what? Where are we getting short wavelength IR from?
You mean in like the example of like the greenhouse, like where you'd be getting it from?
Yeah.
Well, the sun.
Right. We get it from the sun. So high energy, short wavelength. Could short wavelength radiation penetrate easily? Could it pass through the glass easily?
Yeah.
Yeah. So high penetrative ability, right? Low energy. Do you think low energy is short wavelengths or longer wavelengths?
Low energy is long wavelengths.
Long wavelengths. And do you think it could pass through the glass, or do you think it'll be trapped by the glass? Say that again?
I think they'll be trapped.
Exactly, because Jadon, the example with the pan, would the pan be giving off much heat? Like,
No.
if you put your hand around it, you're gonna feel much heat.
No, it would not.
So, and you think that that small amount of heat could easily be trapped? Like, if you were to like close it or seal it, that heat energy can't escape. That is gonna get trapped, right?
Yeah.
When we talk about long wavelengths, we're talking about a very low penetrative ability. So that's just a recap. So Jadon, the sun gives off short wavelength IR light that easily passes through the glass. That would warm up the contents on the inside. So the trees and whatnot will get a little warm. Whatever.
Yeah.
And the trees will get a little warm. And the trees and whatever contents on the inside, they would re-emit long wavelength radiation because they can't emit more energy than the sun, right? So they're going to give off a very small amount of heat, and that's going to be long wavelength, and that can't pass through the glass. That can't pass through the glass. So if it can't pass through the glass, Jadon, is it going to escape or is it just going to get trapped inside?
It'll escape.
No,
It'll get trapped. Sorry.
It will get trapped, right? Long wavelength, remember, has a very weak or low penetrative ability. It can't escape. It's going to get trapped. That's the whole concept about the greenhouse effect. All right. So, Karina, let's move on to evaporation. Give that a read for me.
Evaporation. Evaporation requires heat and is a cooling process. If you come out to a pool in a dry, sunny day, the water on your skin will use the heat energy from your body to evaporate. This prod- products the
Now,
this products
no, this produces.
or this produces the cooling effect.
All right. So
And
let me just try to understand that. All right, Karina, do you think evaporation occurs at a specific temperature, or do you think evaporation can happen at any temperature? Just asking you. What do you think?
I think it can happen at any temperature.
Zachary, do you agree that evaporation could happen at any temperature?
I'm not sure. I think it happens at a fixed temperature.
All right, Zachary says that. Jaden, what about you? Jaden, do you think evaporation happens at a fixed temperature? Jaden,
No, you could hear me, so
you said it doesn't happen at a fixed temperature, right?
yeah, I don't think so.
I would agree with Jaden and Karina. Zachary, let's think about this carefully. Zachary, in that example that we just now spoke about, when you came out of a pool, right, and you had some water on your skin. Tell me something, right, Zachary? If you come out of a pool and you have water on your skin and you're just walking about and whatnot, and eventually the water on your skin would leave,
Yes, sir.
it leaving through evaporation. Is it that the sun is it that the temperature on in Trinidad is 100 degrees Celsius? I mean, I know we just complain it's hot, but do you think it's 100 degrees Celsius?
That's it.
No, and the water does still evaporate, right?
Mm-hmm.
So if that is the case, you think evaporation needs to happen at 100 degrees Celsius, or do you think evaporation can happen at room temperature or at any temperature? What do you think?
Evaporation can happen at any temperature, sir.
Exactly. Think about if you spill water in your room and you're feeling lazy and you didn't mop it up. You think that water will stay there forever?
Not say we evaporate.
Exactly. So you need to understand that evaporation occurs at any temperature. That's one of the key things, right? And evaporation is a cooling process. Because Zachary, when that water on your skin, and that water on your skin would pull heat energy from your skin,
Yes, sir.
and when it evaporates, doesn't it take that heat energy and leaves with it?
Yep.
So if it extracts any heat energy, isn't that a cooling process by definition?
Yes, sir.
Yes, that's why we just call it a cooling process. Right? So Karina, continue reading.
At any temperature, the molecules of a liquid are in continuous random motion with different speeds. Heat is absorbed by the liquid from the surroundings and thus gain Ke, kinetic energy,
Nice.
and moves fast. At the surface, the more and energetic molecules are able to escape into the atmosphere. Since the molecules with the most heat energy escape, this cools the liquid. It should be noted that evaporation only occurs on the surface of a liquid, so depth has no effect or rate of evaporation.
All right. So Karina, let's try to understand everything that we just read. Do you understand most of what you read over here?
Yes, sir.
All right, so from last class, and you know that liquids is move the molecules in a liquid and they move much more freely than in a solid.
Yes, sir.
Okay, great. So you should understand molecules of a liquid, continuous random motion. Should understand that, right? With different speeds. Nice. Then you should understand heat is absorbed by the liquid from the surroundings. Think of if you have water on your skin, right? Right, Karina? If you have water on your skin, that water is gonna, what do you think it's gonna do?
Evaporate or dry.
Yeah. uh, isn't it gonna absorb the heat on your skin?
Yeah.
Yeah, it's gonna pull the heat from your skin, right? So for instance, the water on your skin would absorb the heat that was on your skin, right? So heat is absorbed by the liquid from the surroundings. And Karina, if the water on your skin, right, is absorbing the heat, the water molecules, what would happen to the water molecules? Would they lose kinetic energy? Would they gain kinetic energy? What would happen?
Gain kinetic energy.
Right. And the water on your hand or on your arm, it might move faster, right? So up to this point, we are okay with it. So Karina, then they say at the surface, the more energetic molecules are able to escape into the atmosphere. So Karina, that water droplets on your arm, right? It's gaining kinetic energy from your skin, and the molecules at the surface, the ones that are moving very fast, they are able to escape into the atmosphere. That makes sense?
Yes, sir.
Okay, because remember, the molecules were moving randomly at different speeds. So the ones with the most energy, they will be able to escape at the surface. So I hope you understand that, right? Since the molecules with most heat energy escape, this cools the liquid. So Karina, think about it like this. That water droplet on your arm, the molecule that took the most heat out of from your skin, that's going to leave. So tell me, Karina, if it's taking heat from your skin and it's leaving with it, is it heating you up or is it cooling you down?
Sir, can you repeat? I didn't quite hear.
Okay, that water droplet that's on your hand or on your arm, right? If it's taking the heat from your skin and leaving with it, is it heating you up or is it cooling you down?
Cooling me down.
Exactly, because it's taking the heat and it's leaving with it. Great. So you need to be able to explain evaporation in the exam, right? So you'll say that evaporation is a cooling process, and you'll say at any temperature, the molecules of a liquid and continuous random motion, you will say heat is absorbed by the liquid from the surroundings, and this would cause it to gain kinetic energy and move faster. At the surface, the molecules with the most energy would be able to escape into the atmosphere. That's literally for evaporation. That's it for evaporation. Zachary, you understand that, right?
Yes, sir.
All right, Zachary, which one do you think um is going to evaporate completely first?
The one on the right, the farthest right.
Let me just label it. 1, 2, 3.
So three.
Jadon, do you agree that 3 would evaporate completely first?
Yes.
Okay, I agree. Karina, do you agree?
Yes, sir.
Okay, so we should really label this first. Karina, after that, which one would evaporate right after that?
The one that in a cup.
Mm-hmm. And you notice which one is exposed? Which one is exposed to the air? Like, which one is exposed more to the air? Is it this one or this one? Which one is more exposed?
The one in the cup.
Exactly. Right? So, in other words, the surface area at the top would define how fast it would evaporate. So, Karina, in this instance, and you can see a lot of it is exposed to the air.
Yes, sir.
And then this one is second, and then this one is the last one, right? So one, two, three. So I hope you understand that. So quick recap. Guys, could evaporation happen at any temperature?
Yeah.
All right. Where does evaporation take place? In the liquid or on the surface?
On the surface.
Great. Is it a heating process or a cooling process?
Cooling
A
process.
cooling process.
Great. It's a cooling process. All right. Jalen, can you give me an example of evaporation? An everyday example of it.
Um, like regular evaporation when it comes to like the what do you call this? Like when the sun hits the ocean surface, like that.
Yeah,
Are
that's an
you-
example of evaporation.
Mhm.
Give me another example.
Another one. Hmm. What about like when you're heating water in a kettle
No, that's not evaporation. That is boiling.
that's
Um,
boiling?
although evaporation would take place there, right? That's not evaporation by itself. That's boiling and evaporation. Um, Come on, another example.
Hmm.
So evaporation could take place at any temperature. Evaporation, any temperature. See if you could figure that out then.
What about like cooking? That well, no, that's also like a form of boiling. Um, but like drying clothes count?
Yes, that is a great example. That is a
So
perfect example. Drying clothes.
I thought I fumbled with that one to be honest.
No, drying clothes is a good one,
Mhm.
right? Because you ever notice, right? Like if you hang something wet that's outside and you feel it, is it hot or cold?
It's like oh,
Guys, and all you ever notice that like until the parents probably tell all you don't play in your rain, you get cold.
yeah.
So they hear that, it's
Mm-hmm.
actually Karina, all the
Yes.
parents probably tell you don't go play in your rain when you wet your clothes and you get cold.
Yes, sir.
Right. And when you wet something, like they just say wet clothes or something and they hang it on the line. And the fabric does feel kind of cold. Like when
Yeah.
you come out, like if you come out and like the pool with clothes on, you feel real cool. And the reason for that is because when the wind passes by, right, it takes the molecules. By the way, wind increases the evaporation rate. I'll just say that. And so when they come off the pool, the molecules, the ones with the highest energy, when the wind passes by, it allows it to leave, and that would take heat from you. So that's a good example. So Jadon, try and close as an example of evaporation. Do you know how evaporation happens, Jadon?
It happens.
Yeah.
And that is when well, as you said, not necessarily heat or any temperature, but it's just when the water molecules release from the sitting object, I guess. Because I don't know if I've explained it properly.
Okay,
But
you have the correct idea,
uh-huh.
right? So evaporation, first things first, you need to tell them that so you have to say in a liquid.
Oh my God, sorry. That's like
Yeah. So you have to say in a liquid,
science. This is base science just now.
right? So in a liquid, molecules move about.
And it turns to a gas.
Mm. And so in a liquid, molecules move about
Mhm.
rapidly and in random motion, right? Then you would say heat. So heat is absorbed by the surroundings right? The water molecules with the highest leave at the surface. This is the basic gist of it. So Jadon, in a liquid, molecules will move about rapidly and in a random motion. When you apply heat, or in other words, heat will be absorbed by the surroundings, right? The water molecules with the highest kinetic energy would leave at the surface. That's it. That's evaporation. Right? So let's continue. Right, so as you will see, the other factors that affect evaporation would include humidity, air movement, pressure, and temperature. Yeah. Question, guys. Do you think something would evaporate faster at 10 degrees Celsius or 40 degrees Celsius?
40 degrees Celsius.
Correct, because the water molecules will be vibrating a lot more frequently, correct?
Yes.
Yeah, they would have a lot more kinetic energy, right? Okay, how is evaporation different from boiling? Let's try to figure that out. So guys, and all of us could agree that evaporation can take place at any temperature,
Yes,
Yeah.
sir.
right? So evaporation versus boiling. First of all, evaporation, any temperature. Boiling would only happen at the boiling temperature. In the case of water, what is the boiling temperature for water?
100 degrees.
100 degrees
Right. Evaporation, does it take place throughout the liquid or at the surface?
at the surface.
Right. Boiling would take place
Stir equal water.
right throughout the water. Right. Now, what are the other main differences? Right. That's pretty much it. So evaporation takes place at any temperature. Right. Boiling takes place at the boiling point. When evaporation happens, the temperature would decrease. When boiling happens, the temperature remains constant, right? Because Karina, and for boiling to happen, it needs to occur at the boiling point.
Yes, sir.
Yeah, so the temperature can already change, right? Otherwise, it wouldn't boil. If you understand what I'm saying, it had to remain at 100 degrees Celsius for it to boil.
Yeah.
So that's why I say remains constant. Location, evaporation takes place at the surface, boiling is throughout the liquid, right? And you'd probably see that, Zachary, and when you're boiling water to make a ramen or something, and you just see convection currents, like you would see the water like bubbling and it'd be like rising and going down. You know what I'm talking about?
Yes.
Yeah. So boiling takes place throughout the liquid. And Jadon, with evaporation, Jadon, like if when you're hanging out close to dry via evaporation, do you see any bubbles?
No,
Yeah. When you're boiling water, do you see bubbles?
but yeah,
Yeah. Yeah. So guys, all you need to know these differences, eh? They like to ask this. They might get a table like this on. You need to be able to state all the differences. All right, let's move on now. Right. Guys, do you all understand that perspiration literally happens because of evaporation? Do we understand that?
Yes, sir.
All right, so perspiration is just an example of evaporation. All right, when you perspire, heat is conducted into your sweat, and then it will move out of the body via the sweat gland and duct. The sweat with the heat is then evaporated into the atmosphere. And if it evaporates, the sweat that contained the heat would leave and that would cool your body. Do I need to explain this again? Was everybody okay with perspiration? Jadon, you okay with perspiration?
yeah, I good.
All right, Zachary, you good?
Yes.
Okay. Nice. Moving on to thermal transfer. So before I move on, How could heat be transferred? Give me some. Let me just assess where you all are at. What are the main forms of heat transfer? How is heat transferred? Jaden, I would like you to start more. How is heat transferred? Give me a process by which heat is transferred.
Like radiation.
Yeah, radiation as well. Karina, give me an example of how heat can be transferred.
Kinetic energy.
Nah, that's not heat transfer. That's not a process. So, Karina, talking about like, okay, and heat could be transferred via radiation. Think of like the sun and earth. And heat is being radiated from the heat to earth.
Yeah.
Right? So heat is being transferred via the process called radiation. Right? Think of it, Karina. Think of it like this. How do you cook food?
Using gas.
Okay, I don't mean it like that in a literal sense. um uh Wait is used to cook food, like and is used cooking utensils.
Yeah.
Okay. Let me just say you want to make an egg. Walk me through how you gonna make an egg. Don't say buy a gas tank and pour up, set up the gas tank. No, no, no. Tell me the process. Like how you gonna make an egg?
You crack the egg, you mix it, and then you put it in the pan.
Okay. When you put it in the pan, right? The egg makes starts with C with the pan. Starts with C. It makes what? CON. The egg makes what with the pan?
It cooks.
No,
Yeah.
it makes contact with the pan.
Oh,
Yeah, and you put the egg on the pan,
yeah.
right? So you would say that the heat from the pan is being what by the egg? Like how was that being transferred? Do you have any ideas? Starts with C.
Contact.
Say that again?
Contact.
Not contact, but the heat transfer happens via contact. It's conduction.
Oh, okay.
Yeah. Anytime you have direct physical contact, conduction happens. Think about if you hold a hot spoon, wouldn't you conduct the heat from the spoon?
Yeah.
Okay. And Zachary, I have one more. I have one more.
Um, not really sure anything.
All right. Do you know how an igloo does work?
Say convection.
Yeah, convection.
Hmm.
So let's analyze the medium through which each of these occurs. Zachary, for radiation to happen, do you need physical contact?
No, sir.
Right. No physical contact. Jian, for conduction to occur, do you need physical contact?
Yes.
Yes. Right, Karina, first of all, Karina, do you know what convection is?
I don't think so.
All right. Have you ever heard the saying, like hot air rises, cool air sinks? Ever heard that before?
Yeah.
Yeah, sure, right? I hear that hot air rises.
And coolest thing. So I
Yeah.
do geography.
Right. That's an example of convection. That's convection.
Oh, okay.
Mm-hmm. That would so like let me explain something in an igloo. In an igloo, right? The hot air would rise and the cool air would sink and it would keep recirculating. Let me explain. Let's just say I have some people here. Right? These people would emit heat. The heat that they emit would rise, right? The heat that they emit would rise, the cold air would sink. So Karina, bear with me, right? So Karina, you understand that these people warm, right? These people warm, correct?
Yes, sir.
So they would emit heat. You agree?
Yeah.
The heat that they emit would rise. Now, when it rises to the top, right, Karina, does it stay hot or like does it get cool?
When it rises top, it gets more warm.
No, it's an igloo. It'll get cool. So the hot air,
So,
yeah, tell me.
the igloo is the thing with the ice blocks, right?
Yeah, that's an igloo.
Oh,
Ice blocks.
okay.
Maybe I should get like a proper diagram. Give me a second. Get like a good diagram. Let me know use this get to drawing here.
So
Yeah,
how I learned it, we use the ocean and the sun and a lighthouse.
okay. I'm gonna get like a non-ghetto diagram. All right. Looking for a good diagram. It's key. All right. Let's analyze what's going on here. All right, so Karina, this diagram is also really bad. What about this one? Okay, Karina, the whole point of this is the hot air would rise and the cool air would sink and it would recirculate. A better example to use that probably wouldn't confuse you is boiling. You have to understand this one. I feel like you will understand this. So, Karina, convection happens in fluids, right? Examples of fluids is air, liquids, all that is fluids. Karina, if you're boiling water, right? I just say boiling water. Say with me, right? You're boiling water.
Mm-hmm.
It's the same concept here. Warm liquids would rise and cold liquid would sink because convection works with fluids. So tell me something, Karina. If I'm applying heat at the bottom, what would get hot first? The liquid at the bottom or the liquid at the top?
The liquid at the bottom.
Right. So if the liquid at the bottom getting really hot, that would rise, it would sink.
It will rise.
It will rise. And when it rise and it reach the top, will it cool down? Will it get hot?
It will cool down.
Cool down. And when it get cool, it will sink back down. And
Yeah.
it'll get hot again. And it will rise back to the top. And it'll get cool and it will rise. You understand what happened in there? And
Yeah.
you see this when you're boiling water. Like you probably see the water like whirring about and You're not talking about like you see water around moving.
Yeah.
That's convection currents. So that's how convection works. It works in fluids. Essentially, the hot fluid rises and the cold fluid sinks. And this causes a recirculation of the heat. Zachary, do you understand convection?
Yes.
Did you know that air is a fluid by chance?
So repeat?
Did you know that air is a fluid? Yeah.
Nah, no, sir.
Yeah, air is actually a fluid. You can look it up, right? In fluid dynamics, they literally study
Mm.
air and how air would interact with planes. Air is a fluid. I know it's hard to believe, but yeah, air is a fluid. Liquids are fluids as well, right? Jadon, Selma, you want me to re-explain convection for you?
No, sir, I understand.
All right, so Jadon, let's go. Let's want to go it over one more time. So Jadon, the point is, whatever is hot will rise, whatever is cold will sink. So if I apply a direct heat at the bottom, everything here would get hot or cold,
And that it would get hot.
right? If it get real hot, would it want to stay at the bottom or would it want to rise,
It will rise.
right? When it rises and it reaches to the top, will it cool down or will it get hotter?
Um, it would get hotter.
No.
No.
All right, Jaden. If this is where the flame is, so that's the flame, right? This is the flame. This is like the burner, right? This is the burner.
Yeah.
Where's the pan getting the heat from?
The flame
Exactly. Where's the flame?
under the pan.
Right. So if it gets hot and it rises,
Uh-huh.
is it in direct contact with the flame now?
Oh no, it isn't.
So will it get hotter or will it get cooler?
Cooler.
Right. And if it's cooler, will it want to sink or will it want to rise?
I guess it would like sink.
Yeah, because remember, hot fluids rise and cool
Mm-hmm.
fluids sink. So this would want to sink and it would come back at the bottom. Now,
Mm-hmm.
when it's at the bottom, wouldn't it heat up back again?
Yeah, and it'll be like a constant cycle.
Yeah, it would be a cycle.
Yes.
And that's just going to keep recirculating the heat. So we went through radiation, conduction, and convection. Right. So, Jadon, read that from a thermal transfer processes.
Heat can be transferred from one place to the next. When two objects of varying temperatures are placed together, a transfer of thermal energy occurs from higher to lower temperature in an attempt to get both objects at the same temperature. Example, cold water left in a 30 degrees Celsius room will gain heat from the room and eventually have a temperature of 30 degrees Celsius. The room loses a little heat.
All right.
As a
Let's try to understand that. So, guys, if you don't take away anything from this, I need you to understand that thermal energy always goes from high to low. Always. That's the thermal. That's how the heat gradients. You need to remember that. So heat goes from an area higher temperature to lower temperature. Always. Please know that. Jadon, does the example make sense?
Yeah, it does.
Right? Because Jadon, if you freeze, let me just say you put on like a cold beverage um on your desk, will it remain that temperature?
No, it wouldn't.
Nah, the heat from the surroundings will move to the liquid, and eventually the liquid will reach the same temperature as the surroundings. So it's always from high temperature to low temperature. Zachary and Karina, do we understand the example I note here?
Yes.
Yes, sir.
All right. I want a little look away for a moment. I wonder how good I could trust on him. Like, look away for a bit. Okay, I want you all to tell me Which one is conduction? 1, 2, or 3?
Two.
Right, Jaden, do you agree that 2 is conduction?
Yeah.
Why?
Because he's using the like metal rod to touch the flame, and I guess the heat is also gonna go up the rod, so he's gonna feel it in his hand. Well, the glove or his hand, I guess. The sort of sense. Yes,
Perfect.
no.
You explain that good. Nice. Because you look at both cases, right? He's using this in direct contact with the flame, and he's also in direct contact with it himself. Nice. Karina, which one is 1? What is 1?
Um,
Think about it
so,
carefully.
um, convection,
I like that you say that. Why wouldn't it not be radiation?
because the hot air is going up and then the cool air is coming down.
Perfect. This has to be convection. All right, Jaden, that leaves us with the last one. What's the last one?
Radiation.
Right. Radiation takes place in any direction, right? If you're talking about up or down, that's convection. If you're talking about in any direction, that's radiation. Zachary, you okay with that?
Yes, sir.
So you could just stay on that like thermal transfer notes real quick. I was typing out something.
Okay, no problem. And I'll send these notes after class, like immediately after class. Oh, and um Karina, you there?
Yes, sir.
You have
Okay, so thank you.
no problem. Karina, do you have access to the 17-hour marathon notes? I reference it in the chat. Let me know if you have access to it. Like, can you open it?
So it said it was too large to open out on my phone when I tried to open it.
Oh, shucks. You have a laptop?
Yeah, but it's kind of giving trouble right now.
Oh,
It's,
shucks. Well, here what?
it's
Tell me what your exam is gonna come on, and I'll send you this specific material. What was the exam gonna
okay. Um, well, I know thermal's coming for sure.
right? Okay.
Um, yeah, I think that's mostly the exam this term because you didn't do anything else.
Okay, well,
No.
I'll send all my notes on. I'll send these notes, right? And I'll also send practice questions and solutions.
All right, so um, they had I think it was calculations for thermal.
Okay, noted. Let me see if we can speed up and I'll do at least one calculation. Right?
Okay.
Okay, so this transfer occurs via the three processes: conduction, convection, and radiation. You have it here. Conduction is the transfer of heat through the vibrations of molecules to adjacent molecules. All right. Convection is the transfer of heat through the movement of the medium itself. Radiation is the transfer of heat through the flow of electromagnetic waves. So these are the three processes. You need to know the definition and you need to know examples of each. Right? So I'm going to send these notes. Make sure you take it down and write it down after class. Right. Thermal conductors and insulators. So a thermal conductor is a material that would allow heat to pass through it very easily. Now, it's important to note that conductors are materials with free electrons. Those who are doing chemistry here, have you ever heard about free electrons before?
Yes, sir.
Okay, good. That's also what makes metals electrically conductive as well.
Yes, sir.
and the free electrons, right? So metals will be good conductors of heat because they have free electrons, right? And this will allow efficient transfer of heat. Zachary, if you're wondering why, think about it like this. That free electron could vibrate and spread all over and carry the heat.
Yes.
Yeah, that free electron could move freely and vibrate and send vibrations to the neighboring molecules. And that would allow the heat to be transferred. All right, insulators. They do not have many or any free electrons and may have structural gaps or air spaces that do not efficiently transfer heat, such as cloth or polystyrene. Air is a really poor conductor of heat. Zachary, do you know what a vacuum flask is?
Awesome.
All right, I'm not sure what a vacuum. Does anybody in class know what a vacuum flask is?
Is that like the thing that is hold all the dust?
Say that again. Does he think that is?
Hold the dust in the vacuum?
No, nah. Karina, you know, is that Stanley?
Oh, the cup.
Yeah. A vacuum flask is just basically a flask that would keep something at the same temperature as it. As it. So like all of them Stanley cups is vacuum flasks.
I just call them a flask.
Probably wondering why we just call it vacuum flask. The reason for that is I'll show you why. I'll show you why. Let me get like a good image. All the images on Google like god awful. All right, so this is why we call it a vacuum, right? Okay, and let me show you what a vacuum flask looks like in real life. Zachary, I sure you see this before. Jadon, I sure you see this before. Let me catch
Yeah,
some.
my granny had like 10 of them. She don't
Yeah,
play about she vacuum cleaners.
yeah, all you have to know that's a vacuum flask, right? And a vacuum flask is good at what? What is it good at? So my guys, what is a vacuum flask good at?
Because keep things
Keeping the
some
temperature.
Exactly. And why do you think it's good at that? Let's see. The reason it's good at that is because it have like a little gap, right? Watch. This is where the liquid will be stored, right? And then you have this gap over here. Can anybody tell me what's in this gap?
Eh?
Air. Yes. Yes. Air. Um, Zachary. Karina, this is air. Air. It's nothing here, just air. Right? And why do you think it's
I find that is a real scam. How they go give you a bottle full of air?
no it oh my. Okay, I have my friend gave me a vacuum flask. I'll show you what the vacuum flask looks like. It's remarkable at keeping things cool and hot. It's crazy. It's crazy how good this thing is at keeping things cool. I'll show you all a picture. Look at that. Right? But Karina, if you're going to buy a vacuum flask, right, you should have some expectations. You should know that majority of it is just air and insulated material to keep whatever you put inside cool or hot. You should have an expectation, right? But the one I have, it really not that thick. The wall of it is not thick.
so um it the vacuum flask will be good at keeping these things at the temperature because it wouldn't be able to conduct since it wouldn't really conduct since it have the layer air
Exactly, exactly. That's
and
exactly it.
it's not really a conductor. So
Yeah,
well it,
because
yeah.
Zachary, like, and obviously the walls of this container is gonna get hot or cold.
Yes.
Yeah, but if it's air between here and here, is that heat really going to be able to
It
like
wouldn't be
get
able to
transferred?
transfer. So
Exactly. Wouldn't be able to get transferred. So it's gonna
yes,
be
so that
trapped.
makes sense.
It's gonna be trapped. Yeah. So Karina, this is how it works. We call it a vacuum because there's an absence of air here. I mean, what's in? Let me try to explain this properly. So
Sure, understand, understand.
it's a layer of air, right? It's a layer of air, but there's yeah. But they would have removed the pressure. So it's like a very low pressure. It's a sealed environment. Okay, so you see this region over here? Let me just so Zachary, Jadon, and Karina, until you see this space over here,
Yeah.
Yes, sir.
they would have reduced the pressure, right? Anytime you reduce the pressure, right, and you remove the atmosphere, it's a vacuum. I don't know how else to explain that. All they know is a vacuum chamber by chance. All they know is a vacuum chamber
Yes. So,
where you would like pull like you would reduce the pressure.
mm-hmm.
That's what they would do here. So like you see this area over here is a very low pressure because they would have removed the atmosphere from it. That's what would have happened. Because Zachary, when you're using a vacuum chamber and you're sucking and you're removing and you're literally sucking the air out of the vacuum, I mean of the chamber whatever you put inside, you're
Yes.
removing, you're lowering the pressure. You're lowering the pressure. Right? That's what it did here. That's why it's a vacuum flask. Okay, cool. Oh, watch, what a coincidence. The next thing is vacuum flask. Who would have thought? Wow. Right? So you see, we perfectly lead on to it. So our vacuum flasks work. Right? So vacuum flasks. Right. So as you can see, the vacuum layer is a evacuated space, right? Meaning there's an empty space between the double walls, and this will greatly limit conduction of heat in and out. Because Karina, is air a good conductor of heat? Karina, is air a good conductor of heat?
Yeah.
Yeah. You scare me with that response. You scare me with that response. Zachary, tell Karina the correct thing.
It is not a good conductor of heat.
Is one of the worst conductors of heat possible. Really, really bad. Let me give an example, right? Think of the pan.
Sir, is it because it can't hold any heat?
Yeah, yeah. And air, think of it like this, right, Karina? Think of the structure air. Air is a gas. Gas is gas. The molecules for gases will be moving all over the place. It can't really store much heat, right? Think of the example with the pan. If you put a pan on a stove and you heat up the pan and you put your hand close to the pan, are you feeling much heat? Is the air? Tell me something, Karina. So I'm gonna draw a diagram. Let's just say you put a pan here and you heat up the pan, right? And the pan real hot. You with me?
Yes, sir.
Okay. Tell me something, Karina. If you put your hand over here, are you going to get burnt?
Mm.
You
Slight
don't, you're not,
thing,
you're not touching it, you're just putting your hand over there.
like very slightly.
No, you're not gonna get burnt.
Sure,
Un-
the
Unless
steam from the pan, it wouldn't burn
no,
you.
it don't have no steam in the pan. Just let me just say it have a metal pan And it's that kind of lunatic, so you just pour on the burner and you just heating it up,
Oh,
right?
okay.
There are no steam. So you just put your hand over here. You're not touching the pan, but you have your hand over here. Are you going to get burnt?
No.
Okay. What if you touch the pan?
You'll get burned?
Okay, let's look at the differences there. Right, so Karina, in this instance, you are touching the metal pan. Metal is a what? Bad or good conductor of heat?
Good conductor of heat.
Right, so you're gonna get burnt. If you put your hand over here, what's in between the metal and your hand?
Air?
Okay, is your hand being burnt?
No.
Do you think air is a good conductor of heat?
No.
Exactly. A lot of things in physics could be thought about. Like if you think about it logically, you realize it's not making sense. A lot of things in physics you could do that for. So Karina, think carefully before you say something. Think about it logically. Air is a
All
really
right, sir.
conductor of heat, right? So
Okay.
that's and I don't want you to feel offended or anything. I just say and think about what you say. Think about what you say. Jadon, you too. Jadon, you're notorious for saying things like I feel like if you think about it a bit more, you could be like, nah, this don't make sense. Like when I had asked you if like something, if you heat up something, right, would it emit more energy than it got? Like obviously the answer is no, because you don't like that example with the pan, right? If you heat up a pan,
Yeah.
right, is the pan going to emit a crazy amount of heat compared to like the heat that you supply to it?
No.
No, because Jadon, you literally how much heat you supply into this thing? Like 100 degrees Celsius? Do you think the pan would be emitting 100 degrees Celsius?
No, it would not.
Nah. So the amount of heat that you supply to something, it will be more than the amount of heat being re-emitted by the object. And I understand sometimes the questions will be long and it is have a lot of content there. So by the time I fully ask the question, maybe you forget the first part. That's happened to me. I guilty of that. Somebody would ask me a question and I wouldn't be able to respond because I'll forget what they say in the first part. I understand. I would just think about it carefully before you answer. So this is the general structure of a vacuum flask. You have a cover. Obviously, that will prevent the heat from escaping via convection because Karina, any heat would want to rise, any heat would want to escape by rising.
Yeah.
Yeah, so the cover will prevent that. We have shiny in our walls. The walls are shiny because shiny materials are good at reflecting heat. Did you all know that?
Yes.
Okay, good. So the heat would want to be reflected and it would be trapped. Watch. So like, let me just say a heat wave hit here, it would want to reflect. It hits here, it would want to reflect. So it's just going to keep recycling throughout the liquid. But that's why it's a shiny in our wall. Right? Um, and as you see, helps prevent radiated heat from escaping by reflecting it back into the flask. So Karina, you see what I mean? Like if the heat wanted to escape, it'd be reflected back. So I hope you understand that. Do you?
Yes, sir.
And you can see this is like the vacuum layer, which we just have air in it. Air. And Karina, is air a good conductor of heat?
No.
No. So any heat that escapes is not going to be conducted. It's going to, very little of it is going to be conducted by the outer wall. So most of the heat will be trapped. Nice. All right. Here what? I'm gonna put asterisk by this. We can cover this next class, but I want to do a question with you. I want to do like a calculation question with you, right? Before class ends. Um, Zachary, did you do this in school as yet?
Do what?
You didn't do this in school as yet?
Nah, sir.
Okay, well, I'm gonna troll you into the ocean a little bit here, right? I want to just do some practice. So, Karina, to share this exam. Okay, let's run through a couple of things. Tell a crash course, right? E is equal to MC delta theta. You need to know that. You need to know that E is equal to MLV. And you need to know that E is equal to MLF. You would use this when you have a temperature change, right? Temperature change and no change in states. You would use this formula when you have a change in states, but no temperature change. You would use this when you have a change in states, right? But no temperature change. All right, so Karina, this is what you need to know, right? Like, you need to know these three formulas. Do you know these three formulas already?
She teached it, but I don't think I remembered it.
Okay, well, make sure to remember it for your exam, right? So E is equal to MC delta theta. M stands for the mass, and we know we measure mass in what? What's the SI unit for mass, guys? What's the SI unit for mass?
kg.
kg, right? C is the specific heat capacity of whatever liquid it is. So C is the specific heat capacity. And let me just give out the definition for that first. The amount of heat energy required to raise the temperature to raise by 1 degree Celsius, 1 Kelvin, for 1 kg of a substance. Yeah, or I could just say of a liquid. You know what? I'll leave a substance. Right. So, Karina, that's what specific heat capacity is. Did you know that? Is the amount of heat energy you would need to raise the temperature by 1 degree Celsius or 1 Kelvin for a kilogram of a substance. Did you know that? Specific
No.
capacity. Okay, well, you need to know these things. If they're gonna bring calculations, you need to know these things, right? Another thing you need to know is you need to know what LF is. That is the latent heat of fusion. Latent heat of fusion. And this will be the amount of energy, amount of heat energy required to convert 1 kg of a solid to a liquid. Guys, do you all have access to the formula sheet with all the information? Guys,
So is it?
So
I
it's not opening.
File that you sent?
I would have sent you all a
Yeah.
formula sheet with every single thing you need. Do you all have that?
Nah, so I don't think I
Yes.
have that.
All right.
Same, so
Okay, well, I'll have to send it back. Right. And Karina, you never do any questions using these formulas before at all?
so we did questions, I just never quite understood them.
Okay, I understand. All right, so you need to know what specific heat capacity is. The amount of heat energy required to raise the temperature by 1 degree Celsius or 1 Kelvin per kilogram of a substance. Latent heat of fusion. That's the amount of heat energy required to convert a kilogram of a solid to a liquid, right? And in brackets, no temperature change. So at constant temperature, right? LV, that is the latent heat of vaporization. Right? And this would be the amount of heat energy required to convert 1 kg of a, right? So it's vaporization. So that will be liquid to gas or vice versa. Right? And no temperature change. So here what, Karina, I'm going to do a question with you, right? To make sure at least you have something that you understand. I do like a tricky question. All right, so Karina, I'm gonna do one full question with you, right? Karina,
Yes, sir.
I'm gonna do one full question. I doubt it's gonna be this long in the exam, but it's preparing you for the long run. All right, so Karina, read off my fast.
A student heats 200 grams of ice at 0 degrees Celsius until it turns into steam at 100 degrees Celsius. How much energy was needed to do this?
Okay, first things first, guys. We see in grams. You have to convert grams to what?
Kilograms.
Right, so 200 grams is how much kilograms?
0.2 kg.
Okay, so Zachary and Jaden, we didn't do this yet, but I believe you could still benefit from this a lot. So pay attention. Now, Karina, we are heating a block of ice at 0 degrees Celsius until it turns to what?
Huh?
Say that again?
Sorry, sir, not here.
Okay. We're going from ice to what? Ice to what?
Ice to water,
Right? And then from water to
steam.
nice. So Zachary, do you understand that the changes would happen? Like you would need to go through the phase changes first to then reach 100 degrees Celsius. Think about it, Zachary. It's not like you're going to go straight from ice to steam, correct?
Yes.
Jadon, do you think you could go from ice to steam immediately?
Like in the snap of a finger immediately.
Say that again?
Like in the snap of a finger immediately, or just like
Yeah, you think that could happen like immediately?
mm, oh,
No, I wouldn't say so. Jadon, the
mm,
ice would first have to turn to what?
to like a liquid, and
And then that liquid
to
would then turn to what?
a gas, which is steam.
Exactly. The changes must happen first. So look at how I'm going to do this question. So, Karina, do you understand what I'm saying? The ice wouldn't turn to steam immediately. The ice would first turn to water, then the water would turn to steam, and then the steam would heat up. Come if you're confused by that, Karina.
No, sir, I understand.
All right, so we start off as an ice block. What's the temperature of the ice block?
0 degrees Celsius.
All right. All right, 0 degrees Celsius, nice. From here, that ice will turn to what?
Into water.
What will be the temperature of the water what will be the temperature of the water immediately when it melts?
0 degrees Celsius.
Guys, do you all agree with that? So Karina is saying that the temperature of the temperature of the water immediately after the ice melts is 0 degrees Celsius. Do we agree with that?
Yes.
Jaden, what about you?
Yeah.
Okay. I hope I'm not just saying yeah, right? I know you understand what I'm saying.
Immediately after it melts, it would be how much? 0 degrees?
Yeah, the water.
Um, I don't think so, you know.
No,
Yes.
it would be 0 degrees Celsius.
Say
Think of-
explain that for the latency something.
yes, that this is that same thing. It's the same thing, right?
Yes.
Yeah. Jadon, think of ice, right? When ice melts, does it produce cold water or hot water?
Cold water.
Right. So the point where ice, the immediate point where ice turns to water, right? That water is at 0 degrees Celsius. And then the water will heat up.
Yeah.
Yeah. Right. So Karina, some of you understand that process so far.
Yes, sir.
Okay, was there a change in temperature?
No.
No. So could I use the first formula?
No.
No. Which formula I think I should use? E is equal to MLV or E is equal to MLF?
E is equal to LV.
No, that's for vaporization. Vaporization will be like from a liquid to a gas.
Oh, so
F is
it will
fusion.
be MLF, which is fusion.
Yes. Fusion
Okay.
is when you're going from like a liquid to a solid or a solid to a liquid. Think about it.
Okay.
Fusion. Fusion. You know, like kind of sounds like you're fusing to into a solid or something. Or is that
Yeah.
vaporization? Vaporization kind of sounds like you go into a vapor or gas or something. Right? So for this portion, you're going to use E is equal to MLF because it's going from a solid to a liquid. Okay, so Jadon, now that the ice turns to water, what we could do with this water at 0 degrees Celsius? So remember, Jadon, our goal is to turn to steam at 100 degrees Celsius, right? So what will be the next change? So Jadon, think about it. You turn the ice to water, we're going to do the water now.
Like, heat it up so it will turn to steam.
Okay, is the water going to turn to steam immediately?
No.
No. You're going to heat up the water till the water reaches what temperature?
Wait, you can repeat?
So you're going to heat up the water until the water reaches what temperature?
100.
Right. At this point, Jadon, is it still liquid?
Is it still what? So you're breaking up, sorry.
Okay. Jadon,
Yeah.
at this point in time, is the water still liquid?
No.
It still is.
It still is.
Yes, it still is liquid. Liquid, you could have liquid at 100 degrees Celsius. You'll see where I'm going with this. Zachary, do you understand? Like, okay, this will be latent heat of fusion, right? Um, anytime you're going from one state to the other state, you need some additional energy. You can't just jump straight from liquid to steam. There's a process that happens. So, Jadon, you see how we went from ice at 0 degrees Celsius to water at 0 degrees Celsius?
Yeah.
Think about it. We need to heat up the water first. So the water is going to be heated to 100 degrees Celsius. And then from here, that's going to turn to what?
Steam.
Right. And that steam is going to be at what temperature?
100 degrees Celsius.
Right. So I hope I'm not confusing you, right? So Jadon, let me look at the changes that needs to happen here. So you start off with a block of ice. Ice is solid. You first would need to melt it. Jadon, at the immediate point in time when you melt the ice, the water is going to be at what temperature?
0 degrees Celsius.
Right. Then you're going to do what with the water? If you want to get steam, we would have to do the water first.
Heat it up.
Right. You'd have to heat it up. Think about you actually you want to make steam. And you would put water in a pan and you would heat it up.
Yeah.
Right. The water would eventually reach 100 degrees Celsius. If you continue heating a little longer, then that's going to turn into steam at 100 degrees Celsius. It's going to be a change in state. Right. Karina, on a scale of 1 to 10, how confusing is this?
Not confusing.
So, like, you think you could imagine this in real life? You want to turn a lot
Yeah,
to steam. And the first thing you would do is you would get your tray of ice, you would take the ice, you would put it in a pan, right? And the ice would slowly melt into water.
yeah,
And when the ice fully melts, then the water is gonna start to increase temperature.
yeah,
And eventually the water is going to reach 100 degrees Celsius.
yeah. And
And
turn into steam.
exactly. And you can see this process happening in real life.
Yeah,
Good. So over here, we have solid to liquid, no temperature change. So you use E is equal to MLF. Okay. For this part, is there a change in state?
no,
No. Is there a change in temperature?
yes.
Okay. What formula will I have to use there then?
E equals to MC delta. It was theta.
Right. Delta theta just means a change in temperature. So, Karina, in this case, we went from 0 to 100. So, what was our change in temperature?
100 degrees Celsius.
Right. Cool. Jadon, tell me something, right, Jadon? Did we change the temperature between this and this? That and that step?
No.
Did we change state?
Yes.
Right. So, which formula should I use? E is equal to MC delta theta, E is equal to MLV, or E is equal to MLF?
Um, this one. E is equal to MC delta theta.
No, read this one.
Temperature change. Is that what? Was that I don't have my glasses. Is that our temperature change? No change in state.
Okay. Is that what's happening over here?
No, it's change in state, but keep the same temperature.
Right. You see this one
So
over here?
easy set.
Wait, you see this one, V? That
Yeah.
stands for vaporization. This
Vaporization.
vaporization. And you see this F here, that stands for fusion. So if it's vaporization, I think you could see that that'll be liquid to gas. And fusion, well, it's a vice versa. It could happen either way. So it could be liquid to gas, or it could be gas to liquid. Right? And for fusion, that would be from solid to liquid, or vice versa. So if you understand that.
Yeah, I understand.
Okay, good. So tell me, Jadon, if we are going from water, which is a liquid, to steam, which is a gas, and there's no change in temperature, what should we use?
Um, E equals to MTV.
E is equal to what?
MTV.
I mean MLV.
As a L? I see now dash through the L. My bad. Sorry.
Yeah. I don't know, like when you're writing these formulas, again, you have it writing it fancy. I don't write the L
And
like
cursive.
That's good. So
yeah,
I
yeah.
just never did precision thing.
Well, I don't know. I find like for these formulas that is specifically use a L. I don't know why. But yeah. You can write MLV if you want, but I find it looks better like this. All right. So, Karina, are you okay with me using E is equal to MLV here?
Yes, sir.
Okay, so this will be the entire process, right? Great.
Mm-hmm.
Zachary, you understand the whole process laid out here?
Yeah, I kind of understand. So
You kind of understand what confusing you.
Nothing really. I just yeah, I understand. I understand.
It's just a bit new for you.
Yeah, just a bit new.
All right, but you understand that like look at this, look at this for instance. Obviously, you would have to heat up the water to turn to steam first, sense. You have to heat up the water.
Yes, sir.
Right. Now, is the molecular structure for a liquid and a gas the same?
No, sir.
No. So there's a point in time where there's the same temperature, but you need extra energy to make changes to the molecular structure. And that's where this is coming to play.
Hmm.
Same thing over here. Is solid and liquid the same molecular structure?
No, sir.
No. See, there comes a point in time where it's the same temperature. However, you need to rearrange your molecular structure. So you need this extra energy to do that.
Mm-hmm.
That's the whole process. Right. Let's answer the question now. How much energy was needed to do this? So, Karina, how much, how much changes you see in here?
3 changes.
I see in 3 changes, right? So if you want to find the total energy, you need to find the energy for each one and add it up, correct?
Yeah.
Okay, let's find E is equal to MLF first. And that was the process to go from a solid to a liquid. Let's do that first. 1. E is equal to MLF. What was the mass?
200.
No, it can't
0.2
0.2.
kg.
Oh, what was the latent heat of fusion?
Um, 3.36 times 10 to the power of 5.
That's it, LF. It's not L by F, it's LF. LF means latent heat of fusion. Maybe I should write it a bit smaller. Right. Plug into your calculator and let me know what you're getting. Your answer will be in joules, because energy is measured in joules. Until you remember like the Cannon-Boren experiment and James Joules and all that. But you're not talking about? Exactly. Remember the Cannon-Boren experiment with
Yes, sir.
Count Rumford and all that? Okay, good.
Yes, sir. Yes, sir.
Yeah. All right, so plug that into the calculator and let me know what again, right, for the energy. So 0.2 by 3.36 by 10 to the power of 5. As soon as one of you all get an answer, tell me.
67200 joule.
6767. What?
Oh my,
I
for
didn't plan
gosh
that.
sake.
I
I
didn't
now
plan
get
that.
off my head.
I, di-
Now get off my head.
I didn't plan it, I didn't plan it. That's just how the universe is worked. 6 7. Damn, that's crazy.
You know
That's
how
really,
much times I keep hearing that from my friends whole week? Trying
yeah.
to process it out my head.
And then they come to class to like to be intellectually stimulated and then they hear 6 7 again. Ah,
Yeah,
that's stupid.
exactly.
I didn't come up with this question, no. This question just has to happen to be like this. You can't escape 6 7. Right. Let's figure out the energy for the second process. E is equal to mc delta theta. Right? The full formula for this is E is equal to mc, right? Temperature 2 minus temperature 1. That's what delta theta means. Delta theta means change in temperature. Delta theta, change. Zachary, what do you think temperature 1 is for the second process?
0 degrees Celsius.
Right? And the second temperature is 100 T2.
Yeah,
What was the mass?
0.2.
All right, Jaden, what was C? Remember, C is the specific heat capacity, yeah? C stands for the specific heat capacity. What did they give us C to be? Yeah. and then here in Geelong. But it's given there. The specific heat capacity is 4,200. So this is C, right? This is LF, and this is LV. Right, so 4,200. And then that'll be T2 minus T1, which is 100 minus 0, which is just 100. So plug that into the calculator and let me know what you'll get in. So 0.2 by 4,200 by 100.
84000.
84000.
Yes.
Yeah.
84000. 84,000 joules.
Yeah.
Okay, let's find the energy in the last process, which is when it went from water at 100 to steam at 100. Right? In this situation, is there a change in temperature?
No.
No, I don't have a change in temperature. Right? So we can't use E is equal to MC delta theta. We're going to use E is equal to MLB. Right? What is the mass?
0.2.
Right? What is LV?
2.25 times 10 to the power of 6.
Right, so Jada, now way to plug this in and tell me what you're getting. Jada, let me know if you're there.
Wait, hello, sir?
Yeah, Jada, now way to plug this into the calculator and let me know what you're getting. The rest of you guys will
450,000 joules.
450,000.
Yes.
Right. One of you guys verify that too.
Yes, sir.
Okay, good job, Jadon. Right, so Jadon, if I wanted to figure out the total energy needed to go from ice
Mhm.
to steam, how much that will be?
Total energy to go from ice to steam.
Yes. So let's look at what happened, right, Jadon? So we calculated the energy to go from a solid to a liquid. How much energy was that?
How much energy? That was 67,200.
Right. Right. Okay, so that was the energy needed to go from here to here. What about from here to here?
84,000.
And this one?
450,000.
So what would be the energy to go from ice to steam?
So that you just add it up.
Yep, that's it. Right, and you would say ET, which means total energy. They can say ET.
601, 601, 200. 601,200.
Right. It was, say that one more time.
Let's not just double check.
601200.
601200.
Yes,
Yeah.
sir.
Right, that's it. So Karina, we think about this question. The hard or like if you get this correct.
So I find it was pretty easy.
Yeah, this is one of the more complete questions. Normally, Karina, normally they might this is what they might do, right? They might be like find the energy. Zachary, I know you didn't do it fully yet, and Jada, but how the find this was?
So it wasn't that bad.
It's gonna be like
So,
a 8 mark question in the exam.
so in
Yeah.
like actual CSEC, when they give you this question, right?
Mhm.
Would they give you the keys for the latency
Yes.
and the
Yes, they would.
okay.
Yes, they would. They don't expect you to remember that. That kind of crazy.
They expect us to remember 273 Kelvin.
Okay, that's not that bad. That's not that bad. Okay. Yeah. And if you want, you could always store that in your calculator and recall it in the exam. I could show
I
you
feel I would do that. I feel I would do that.
that. Yeah, boy. All right. This is a question they might ask you in the exam. Find the energy to go from, let me just say -5, to go from -5 degrees Celsius ice to 20 degrees Celsius water. I think once you could figure out the changes, you could calculate the energy. So let me just figure out the changes for this question. We're not going to do the full working. If you want, you can do the full working for homework. But let me just see if we can figure out the changes. I know, like, send it to me. Right, it's a little bit neater.
The ice,
So, all right, so yeah, tell them ice to ice.
and then ice to water
Wait, let me just try it. So ice, at what temperature?
at -5 degrees Celsius.
Right, that go into what?
Ice to 0 degrees Celsius.
Jadon, you okay with everything so far?
Yes, sir.
All right. Jadon, make a guess. What do you think? So if you had ice at 0 degrees Celsius, what are we going to do next?
It turns to a liquid.
At what temperature?
Um, 20 degrees Celsius.
No, no,
Zero.
no, it's
Zero.
zero. Remember, Jadon, at the instant point where ice melts, okay, Jadon, if you put an ice block in your hand, will that water be 37 degrees Celsius right after it melts?
No, it wouldn't.
No, that ice gonna be cool. It's gonna be cold water. Cold water, right? Cold water. Lock that in,
Yeah,
right?
a lot in trust.
Right? So that'll be water at 0 degrees Celsius. And Jadon, now that the ice fully melts, what we could do next with our water?
You said you asked what is the next process?
Yeah, so after the ice fully melts to water, what we could do with our water now?
I guess leave it at, or like, well, you want it to be at 20 degrees Celsius, so you could just like leave it till it becomes room temperature.
Yeah, you could leave it and monitor the temperature, or you could like apply like very, very small amounts of heat
Mhm.
and monitor that. Yeah. All right. So Karina, you feel like you understand this perfectly?
Yes, sir.
All right. Zachary, what about you? You feel like you understand the changes?
Yes, sir.
Okay, good. Tell me guys, what formula would I use to calculate the energy required to go from ice at -5 to ice at 0?
LF, sir.
The wait, -5 to 0.
Yes. Okay, Zachary, you said MLF.
Sir, I don't think that's correct.
Let me run through the formulas, right? Okay, so E is equal to MC delta theta. Delta theta means change in temperature. So you use this one when you have a change in temperature,
Well, yes, sir. That's the one you would use.
right? You use this one when you have a change in temperature and no change in state. The other one, right, is E is equal to MLF. You use this one when you're going from its fusion, so solid to liquid, right? And there's no change in temperature. And where's the last formula, Karina?
The last formula for is E equal to MLV
Right, and you would use that when you're going from what to
for
what,
you for liquid to steam or liquid to gas.
right? Right, and there would be again no change in temperature. All right. Zachary, correct yourself. Which one we gonna use for the first procedure? The first process.
E MC delta, whatever.
E is equal to MC delta theta, whatever. Right? E is equal to MC delta theta. Do you know how you would find delta theta?
So you would the temperatures.
Right. So that would be
Temperature 1 minus temperature 2.
right. So that would be 0 minus what?
-5.
What is 0 minus -5?
+5.
Right. Great. Okay. Guys, what would I use for the second process? Ice to water at 0 degrees Celsius.
E equals MLF.
Right. What would I use for the last process?
E equals ML.
Nope.
E equals MC delta theta.
Yeah, anytime you see a change in temperature, you have to use E is equal to MC delta theta.
Yes, sir.
Right. So Karina, I think you'll be able to do the substitution correct and add everything together to get the correct answer.
Yes, sir.
Okay, great. So yeah, just like that, I think you could secure like a good amount of marks there. And well, I will send the rest of the document and I will send the past paper questions. So you should be in our game. Practice and it will be fine. All right. So yeah, guys, that's it for class today. Do you have any questions?
No, sir.
All right, before I go, Jadon, I'm looking at you now. Tell me, short wavelength, short wavelength IR radiation. Where does that come from? Where does short wavelength IR radiation come from?
Where does it come from? The sun.
Yeah, the sun. Is it low energy or high energy?
Um,
It's coming from the sun.
it is high energy.
You think it could easily pass through glass?
Yes.
Right? Easily pass through glass. Right, Jadon, when it enters the glass, right? What are you
Mhm.
gonna do with the contents inside the glass house?
It going to up the contents inside. So I guess the trees and then
You're gonna
sort of
heat it up, hence,
yes.
right? And those trees, are they going to emit plenty heat or like emit a little bit of heat?
A little bit.
A little bit of heat, right? So they're going to emit short wavelength IR radiation
Mhm.
or long wavelength IR radiation. If they emit a little bit of heat,
They release long wavelengths.
right? Right, and that will come from the objects re-emitting the heat.
Mhm.
That'll be low energy, and it will be trapped because it can't pass through glass. Great. Zachary, if I ask you a question from the whole of class today, you should be able to remember it, Hans.
Yes, sir.
Okay, let me test here. What's the name of this?
Bimetal.
Bimetallic strip.
Yeah, bimetallic. Yeah.
Okay, if I tell you A is the softer metal. A is softer metal, right? And I apply heat. Apply heat over here. Which one is gonna expand more?
E will expand more soon.
Will B expand as fast?
Mm-mm.
So what will happen to the shape of it?
It will curve downwards.
Right, it will curve downwards. Right? Because this one cannot pull in it now. It cannot pull it in.
Yes, sir.
Right? Karina, which one would be more prone to conduction? I mean contraction.
A.
A as well, right? Because A is very sensitive, it's a soft metal, right? Its feelings gets hurt very easily. Yeah. Okay, great. So we understand that. Where would I use this? Jadon, where would I use a bimetallic strip?
You would use it in a fire alarm.
Right? Is evaporation and boiling the same?
No, it is not.
Tell me one difference.
One difference between evaporation and boiling.
Yeah.
Um,
One difference.
boiling evaporation is no, that's not different. Kind of brain stuck, you know.
All right. Jadon, what temperature does boiling occur at?
Boiling occurs at 100 degrees Celsius.
What temperature does evaporation happen at?
It, uh,
Does it occur at any particular temperature? It could occur at any temperature.
no, any temperature, sorry.
Right. So that's a good one. That's a good one to use. Think about it. If you have AC in your room, right, and you spill water on the floor, you're not gonna it's because your room cool, right? But the
Mhm.
water is not gonna remain on the ground. It's still going to evaporate eventually over time. So
Yeah,
evaporation could happen at any temperature. Boiling
okay.
happens at the boiling point. Right. Karina, give me one difference between evaporation and boiling pass.
Take a repeat. You're kind of bringing up for me now.
Give me an example. Give me a difference between evaporation and boiling.
Evaporation is on the surface of the water, and then boiling is out the water.
Right. So Karina, evaporation literally says it's not that deep, bro. It's not that deep. That's evaporation. Yeah. I don't know if you get a joke, but yeah, I do tell really bad jokes. Right. You
I got it.
probably cringing in the back there. All right. Zachary, you have any other differences you could list? Or like,
Um, um, for boiling, bubbles is present and evaporation bubbles are not present.
okay, great. Great. So yeah, I think that's it. Everybody understand what we did today in class? Everything?
Yes, sir.
Okay,
Yes,
nice.
sir.
Karina,
Yes, sir.
Yes, sir.
um, Karina, tell me the three formulas you're supposed to know for your exam Monday.
E equals MC delta theta.
Okay, what is delta
E
theta? How about you find delta theta?
temperature 1 subtract temperature 2.
No, no, no. Zachary, tell us the correct thing.
So what?
She said temperature 1 minus temperature 2 with delta theta.
So it's temperature 2 minus temperature 1.
Yeah, don't forget that, Karina. Otherwise, you get negative answers. You don't want negative answers. Trust me. Right? T2
Okay.
minus T1. T2 minus T1. What's the other two
Okay.
formulas? Tell me fast.
E equals MLF.
Well, when would I use that one? When would I use that?
That fusion is solid to liquid.
Right. Would I use it when I had
And
change in temperature?
no.
No. Okay, what's the last one?
And then there's E equals MLV, which is liquid to gas.
Okay,
And
nice.
there's no change of temperature.
Great. So it sounds like everybody have everything we did today locked in. Nice, man. So yeah, I hope all have a blessed day. Right? Later, guys. Bye.
So
Yeah, tell me.
the maths homework, I did not get it because you added me to the chat after sending it in the group chat.
Hmm. Okay. Uh, let's check. Okay, I will send you the document, right?
Okay, thank you, sir. Bye.
That's a problem. Have a blessed day.